Hi, today we're going to go through the PAT paper from 2009 looking at the first 5 multiple choice questions, 13 through 17. Okay, so question 13 says that the sun produces 3 times 10 to the 26 watts through fusion. And we're asked how much mass is it losing per second. Well, this draws upon Einstein's famous equation, E equals mc squared. Because we've been given some equation to do with power, or energy, and well, we're asked how the hell we can relate that to mass. And the only way we know to do that is by using our equation E equals mc squared. Now power is in units of watts, so that's energy per second. So clearly if we just use we want energy per second, so you want E over T, and E over T is just watts. So we can simply replace the E with 3 times 8 to 26 watts. So we want 3 times 8 times 10, 3.8 times 10 to the 26, divided by C squared. Well, C is 3 times 10 to the 8 squared, and that is the amount of mass it loses per second. Well, that's 3.8 times 10 to the 26 over 9 times 10 to the 16. Well, that's 38 times 10 to the 25 over 9 times 10 to the 16, and that's approximately equal to 4 times 10 to the 9, and that's in kilograms per second. So that gives us the answer of A, which is 4.2 times 10 to the 9 kilograms per second. So question 14, we're told that a battery is replaced by 2 identical batteries in parallel. And we're asked which of these 4 options what happens to the current, the maximum voltage and the maximum current in this combination. Which of these 4 options gives the correct changes? Okay, well that means we're basically going from a battery like this to a parallel combination of the same battery. Now what we know about parallel combinations is that the voltage is the same in both branches. So if the voltage for this was V, then the voltage from here to here is also V. Because they're in parallel and the voltage potential difference is from this point to this point. It essentially is identical in each branch. It doesn't split. So that means immediately we can cross off D as our answer because it has V max being higher. Okay, well the only way to think about it is the current. So what do we know about current? Well, current is voltage divided by resistance. So we've deduced that the voltage is the same. So should we think about what the resistance is? Well, when we add in series, in parallel, we add the reciprocals. Say we called this of resistance R. Well, each of these has resistance R, but this resistance-wise would be the same as the sum of their reciprocals, and that's equal to R over 2. So in fact, the resistance goes down. And what you see here, we're dividing by a smaller resistance now, which means that this actually goes up. So in fact, the current must increase, which leads us to the answer of C. Okay. So question 15 says the moon Titan has an angular diameter of 4.4 milliradians as seen from Saturn, and the sun has an angular diameter of 9.3 milliradians as seen from Earth. And we're asked which of these following things cannot be seen from the surface of Saturn. A lunar eclipse of Titan by Saturn, B, a partial solar eclipse due to Titan, C, a total solar eclipse due to Titan, and D, an annular solar eclipse due to Titan. Okay, we'll start by drawing this. So let's start by drawing Saturn here, and then Titan, one of its moons. This is not to scale, by the way. And then here's the Earth, and then here's the Sun. Okay, so an angular diameter is essentially this angle here. If we were to draw a line from here to the edge of Titan, this angle here subtended will be the angular diameter. So it's 4.4 milliradians. And similarly, from Earth to the Sun, without that crossing over, would be 9.3. Okay, so let's go through these. So a lunar eclipse of Titan by Saturn. So that basically means a lunar eclipse is when the moon appears darkened as it passes into the Earth's shadow. So from the point of view of Saturn, that means Titan will be darkened as it passes in behind Saturn. So that means this would go here, behind Saturn, and then the light from the sun would be blocked, and Titan would be darkened. Well, clearly we see this can happen, because the angle here is so small. I mean, Titan is so small compared to Saturn that it will be completely covered out by the sun's light. So A can happen. B, a partial solar eclipse due to Titan. Well, clearly we see here Titan's in front of Saturn is partially eclipsing the sun, so this clearly can happen. Well, let's see, a total solar eclipse due to Titan. Well, based on the angles subtended, and we see, this is roughly to scale in the sense that the angle here is much larger. You will see that you can never have Titan fully eclipsing the sun. The angular diameter of it is simply too small. So C can't happen. And D, an annular solar eclipse due to Titan. Well, an annular solar eclipse is basically when the moon blocks out the sun and a ring of light forms around, an annulus forms around the moon. Due to the size of Titan compared to the sun, i.e. being smaller, this can happen. It's essentially the same as B. So D can happen. So that means our answer is going to be C. This is the one that can't happen. So question 16 says a yacht on a lake drops its anchor overboard and asks what happens to the water level. Now, anything to do with fluids and floating and sinking is all to do with something called Archimedes' principle. If you haven't seen our video on this already, I would recommend you watch it. It explains the principles about floating and sinking much more clearly and much more thoroughly. But essentially, the idea is that a fluid, when an object is partially or fully submerged in a fluid, the buoyancy force it experiences is equal to the weight of the fluid it displaces. So if we just quickly sketch out our boat. So we have our boat here. This is from a front. So we're looking forward at our boat. So it's in the water like this. And we're looking at it this way. So it's only displacing this much fluid, but it's floating, which means that the amount of water it's displacing is equal to the weight of the boat. So it's able to counteract its weight, a buoyancy force large enough for it not to sink. So when the anchor's in the boat, the amount of water being displaced is equal to has a volume that will be heavy enough to counteract the weight of both the anchor and the boat. Now clearly, as the anchor is a lot denser than the water, the amount of water that has to be displaced to produce a buoyancy force to counteract the weight of the anchor is a very large amount of water, a lot larger than the volume of the anchor. Now when you drop the anchor into the water, the weight of the boat drops slightly. So the volume of water it displaces will drop slightly. But the amount it drops will be equal to the weight, will be equal to a volume of water that will have the same weight as the anchor. And clearly that's going to be a very large amount of water. And when the anchor's in the water, it's going to sink, as we know. So the buoyancy force produced by the water will not be large enough to counteract its weight. So the volume of water the anchor displaces when it's in the water is actually only equal to the volume of the anchor itself. So when the anchor is in the water, it is going to displace only its volume of water. And the boat will displace a volume of water equal in weight to the volume of the boat. But when the anchor is in the water will be displaced such that it counteracts the weight of both the anchor and the boat. And clearly that's going to be a lot more water. So the idea is when the anchor is dropped into the water, the level of the water will fall as a smaller amount of water is displaced. So the answer is C, the level of the water will fall slightly. So question 17 says that water falls from Felbeck into the gaping gill pothole. So essentially what it's asking us is, can you estimate the temperature change of water falling 105 meters? So the assumption we have to make in this question is that the change in energy of the water, we know for a fact that Q is mc delta T. We're going to assume that this change in energy Q comes from the change in gravitational potential energy. So we say its loss in gravitational potential energy will be equal to its change in internal heat. So what we're going to do is equate them. So our change in gravitational potential energy, delta EP, will be equal to delta Q. Delta EP, well, that's going to be mg delta H, the height it fell, which will be equal to mc delta T. So clearly we see the mass is actually irrelevant here, which is why they haven't specified the amount that falls. So we get delta T is equal to G delta H over C. Well, G is 10, delta H is 105 meters, and C, we're told, is 4.2 kilojoules per Kelvin per kilogram. So that's 4.2 times 10 to the 3 joules. Putting it in standard units. And well, that's equal to 1050 over 4.2 times 10 to the 3, which is approximately equal to 0.25 degrees Celsius. So the answer is B.